Hey guys, and we're back. We're going to pick up with reaction mechanisms. So I hope that you didn't have any issues with the first videos. I've yet to really see a lot of posts asking questions about the first lecture, so I'm going to assume that means that you guys all understand. All right, so we're moving on. So reaction mechanisms, right? We talked about the problem with a balanced chemical equation. So if we click down and we make all this reveal, right? The problem with a balanced chemical equation is it only shows you where you started and where you ended. And sometimes a reaction can happen in one step and that's it. But most reactions actually take multiple steps. There's a sequence of events that's taking place. And whenever there's a sequence of events taking place, none of the intermediate steps are being represented at all in a balanced chemical equation. All the balanced chemical equation does is tell you basically the beginning or the first chapter of a book and the end, the last chapter of a book. You miss the entire middle of the book. So what the mechanism does when we study mechanisms is it lets us study the rest of the book, right? The actually interesting stuff that's happening here where the bonds are being broken and sort of atoms are moving around and things like that. Okay, so let's look at a reaction mechanism. So here we have a reaction mechanism. So the reaction is in red. Okay, so we've got hydrogen gas reacting with 2 moles of iodine chloride gas, and then 2 moles of hydrochloric gas, and then iodine gas. Okay, now this cannot happen in a singular step. And the problem with that is very rarely, if you look here, you essentially have 3 reactants. You have hydrogen and you have 2 moles of ICl. This is a 3 reactant equation. That doesn't tend to happen in one step. And in fact, here is the mechanism. It happens in 2 steps. So what happens is the hydrogen reacts with one of the ICLs. Hydrogen reacts with Cl to make HCl. The other hydrogen reacts with iodine to make HI. But notice HI does not appear as a product because we're then going to take that HI, react it with the other ICl. H reacts with Cl to make another HCl, and I reacts with I to make our iodine. Okay, so HI was made in the first step, immediately consumed in the second step, and it does not appear at all in the balanced overall equation. So what we call HI is we call it an intermediate. Okay, so an intermediate is something that's formed in one elementary reaction and then immediately consumed in the next or consumed in a following one, and it doesn't appear in the overall balanced chemical equation. Okay, so in this case, HI is an intermediate. All right, now each step within a mechanism, though, is an independent reaction. Okay, each step is what we call an elementary reaction. And as I mentioned last lecture, if you know something is an elementary reaction, then you can assume that the coefficients are the exponents within the rate law. Okay, so if we look at our 2 steps here, H2 plus ICl. So all rate laws begin with rate equals K. Now, I'm going to call this K1. Why? Because I'm trying to differentiate that this K and the K from the other rate law are going to be different numbers. But it doesn't really matter if you put the 1 or not. You can put K, right? Times the concentration of the reactant. Since I know it's elementary, it's raised to its coefficient. If it has no coefficient, it's first order, which we don't represent. ICL is the same way, right? Times the concentration of ICL. Again, no coefficient, so it's raised to the first order. And then the second one is exactly the same way. Rate equals K times the concentration of HI times the concentration of ICL. So we can write and predict the rate laws for these 2 steps because we know they're elementary reactions, but this is not an elementary reaction in red. So I still don't know what the rate law of this is. But that's where we're going to get to. That's where we're heading. How can you use the 2 rate laws that you already know to determine the rate law for the reaction that you don't know? You know the 2 of them make up this equation in red, so surely we should be able to use the information we already have to determine the rate law. for the reaction in red. And that's exactly what we can do. But let's talk about how. Let's talk about how we can do that. And before we get to that, let's talk about a little bit more terminology, okay? So the number of reactant molecules in an elementary step is something that we call its molecularity, okay? So if you only have a singular reactant and you only have 1 mole of that reactant, we would say that is a unimolecular process, okay? Here's an example. Unimolecular. Now, what if you had a singular reactant, but you had 2 moles of it? Or you had 1 mole of 2 different things? That would be a bimolecular process. And here are some examples of rate laws for those. Okay. Now, what did I say on the previous, or a couple of slides ago, that when you have 3 moles of reactants, that's rare. And here's the book saying I'm right. Okay. Whether that be 3 moles of the same thing, or in our example where we had 2 moles of one thing and 1 mole of another, right? Or 1 mole of 3 different things. In all 3 cases, that is a termolecular process, termolecular, and these are rare, okay? Rare processes to occur in a single elementary step. We know this can happen, but it's rare to happen in a single step. It's more likely going to be a mechanism. Let's do some practice before we move on and we talk about how to predict rate laws for mechanisms. So here we have the 2-step mechanism of the conversion of ozone, which is O3, into regular oxygen, right, which is diatomic oxygen. Well, the first thing that happens here is ozone decomposes into oxygen gas and a single oxygen atom. Then that oxygen atom is going to react with another molecule of ozone to generate 2 more moles of oxygen gas. So first thing, let's determine the molecularity of each of these reactions, okay? So if we look at the first reaction, we have a singular reactant, and we only have 1 mole of it. So that is unimolecular, right? And then if we look at the second one, I have 2 reactants, 1 mole of each, 1 plus 1 is 2, and we refer to that as a bimolecular process. Now, this is a mechanism. What is the overall reaction that this mechanism is representing? So how you do this is you're literally just going to add these 2 things together. So make sure the arrows are lined up as they are. So 1 mole of O2 plus another mole of O2 gives me 3 moles of O2 on the right, gas. Now I have a mole of a singular oxygen on the right, but I also have a mole of a singular oxygen on the left. So what that means is these 2 are going to cancel each other out. So they will not appear in the overall reaction. We have a name for that. What's the name for something that doesn't appear in the overall reaction? Something that's produced and then consumed. Yes, it's an intermediate. Okay, very good. And then 2 O3s, we got 2 moles of O3 as our reactant, decomposing into 3 moles of O2. It is balanced. 2 times 3 is 6. 3 times 2 is 6, right? And as we've already said, the intermediate in this case is the singular monatomic oxygen. Now, let's go a little step further and I know it's not on the slide, but let's talk it through. What would the rate laws of these 2 steps be? If I'm telling you that these are elementary reactions, you should be able to predict the rate laws for them, okay? So remember, every rate law starts with rate equals K. In this case, there's only 1 reactant. So bracket O3 raised to, there's nothing here, so it's an assumed 1 and you don't even have to write it. So rate equals K times concentration of O3. That's it. What about this rate law? This one would be rate equals K times the concentration of O3 times the concentration of O. Pretty easy to do when you know it's elementary. But how in the world do you do it otherwise? Like, take a look at this example. If we assume that the following reaction occurs in a single elementary reaction, so meaning this is a 1-step process, this right here, 1 step. It's only bimolecular, so could be one step. Not rare for it to be one step. If we predict the rate law here, it's going to be rate equals K times the concentration of H2 times the concentration of Br2. All right, that's what we predict if it was elementary. So now let's assume we went in the lab and we actually ran our experiment and we determined the exponentials, and hydrogen was 1, but it turns out bromine wasn't 1. We get a half for bromine experimentally. What does that mean? Well, really the only thing you can say at this point is it ain't one step. You have no clue how many steps it is, but you know it has to be a mechanism, and it cannot occur in a singular step because what you predicted off the coefficients, since it doesn't line up with the experiment, it's not a one step, it's not an elementary reaction. So we could have anywhere from 2 to, whatever number of steps. There's really no way to predict the number of steps. Probably not that many in this case, but nonetheless, not a single elementary step. All right, so now how do we predict these rate laws of these multi-step processes? Well, just think about it. Whenever you do group work, you all have a contribution to participate in this group work assignment, but you're not all contributing at the same pace, right? I know when I did group work when I was younger, I would get frustrated because I always felt like one member of our group just held us back. They either didn't do what they were supposed to do or just were super slow, right? It's the same thing with chemical reactions. There's always going to be a slow step. And we call the slow step the rate determining step because the slow step's what's holding you up, right? So a textbook that we used to have represented this as traffic plazas. Okay, first of all, let me recommend if there are toll plazas this close together, don't take that road because they're just ripping you off and taking all your money. Okay, but nonetheless, if we look in the first picture, it looks like most of the cars are being held up here at Plaza A. So the slow step or the rate determining step is the first plaza. But if we look at the second example, now it looks like the cars are starting to bundle up at Plaza B. So in this example, the slow step or the rate determining step is the second toll booth. Okay? So what we're saying is we need to know what the slow step is because the slow step is what's determining the overall rate. So if we know the rate laws of both steps and we can figure out which one is the slow step, then we can determine the rate law of the overall mechanism. Okay, and that's what we're going to do in the next video. So into video 1, I will see you guys in video 2.